In this example, we will find the solution to the linear system of differential equations y prime equals -2, -3, 3, -2 times y. We start by finding the eigenvalues lambda1 and lambda2 as the roots of the characteristic equation, which is given by 0 equals the determinant of a minus lambda I, where a is our coefficient matrix, -2, -3, 3, -2. So this is the determinant of -2 minus lambda, -3, 3, -2 minus lambda, which comes to lambda squared plus 4 lambda plus 13. We won't be able to factor this quadratic, so we'll need to use the quadratic formula, which gives us that lambda, 1, and 2 are -4 plus or minus the square root of 4 squared minus 4 times 13 all over 2. Simplifying what we have inside the radical, we'll have 4 squared is 16 minus 4 times 13, which is 52, to give us -36. But this means we'll have complex solutions for our eigenvalues, -4 plus or minus 6i over 2, which reduces to -2 plus or minus 3i. So how do we find a solution to our system of differential equations if the eigenvalue is complex? Recall, for a matrix A with eigenvalue lambda and eigenvector v, we showed that y equal to e to the lambda t times v is a solution to y prime equals a times y. In this computation that we did to prove this did not rely on lambda and v being real. So if we can find an eigenvector for lambda 1 equal to -2 plus 3i, then we can find a solution. To find the eigenvector for lambda 1 equal to -2 plus 3i, we'll need to go back to our definition of an eigenvalue and eigenvector. We'll take the eigenvector to be unknown constants a and b, and then we need our matrix A times v to be equal to our eigenvalue times v. So we'll have -2, -3, 3, -2 times the vector AB is equal to -2 plus 3i times AB. Multiplying our eigenvalue in on the right-hand side, we'll have -2 plus 3i times A and -2 plus 3i times B. On the left-hand side, doing our matrix multiplication, we'll have -2a minus 3b and 3a minus 2b. And just as before, this will give us a relationship between a and b. Since these two vectors have to be equal, we know that their top components must be equal. So -2a minus 3b has to equal -2 plus 3i times a. But that right-hand side is -2a plus 3a times I. So adding a to both sides gives the relationship -3b equals 3a times I. And dividing by -3 gives us that b equals -ai. And finally, we can get rid of that negative sign here by multiplying both sides by I. On the left-hand side, we'll have b times I, and on the right-hand side, we'll have -a times I squared, which is just a. So we get the relationship that a has to equal b times I. And we can pick b to be 1, giving us the eigenvector I1. So the differential equation has some complex solution y sub c of t equal to e to our lambda value times t, e to the -2 plus 3i times t, times the eigenvector I1. While this is great that we found a solution, notice that our original differential equation was all real, but our solution is complex. So how do we get a real solution to our real differential equation from this complex solution? A theorem about complex solutions will help us find these real solutions that we're looking for from this complex one. The theorem states that if y sub c of t is a complex solution of a linear system of differential equations y prime equal to a times y, and if y sub c can be written in its real and imaginary parts, yc equals yr plus I times yi, where yr and yi are real valued functions, then both yr and yi are also solutions to that original differential equation y prime equals ay. I want to point out here that even though we call yi the imaginary part of y, it is a completely real function. We call it the imaginary part because of its coefficient I, but yi itself is completely real. While we won't prove it here, this can be proved by comparing the real and imaginary parts to plugging in our solution yc equal to yr plus I times yi in the differential equation. But using this theorem, if we can write yc equal to e to the negative 2 plus 3it times I1 in terms of its real and imaginary parts, yr and yi, then these will both be solutions to our original differential equation. And if we have these two solutions, yr and yi, then we can build the general solution, y of t equals c1 times yr plus c2 times yi. So all that remains is to write yc equal to e to the negative 2 plus 3it times I1 in terms of its real and imaginary parts, yr plus I times yi. To write yc in its real and imaginary parts, we'll start by writing each of the factors e to the negative 2 plus 3it and the vector I1 in their real and imaginary parts. For the vector, we can easily split I1 into its real and imaginary parts by writing I1 as 0, 1 plus I0. And then in the vector I0, we can factor out I, so we have 0, 1 plus I times 1, 0. The vector 0, 1 is the real part of our vector, and the vector 1, 0 is the imaginary part. Again, even though it's called the imaginary part, it is a completely real vector. Just its coefficient is I. Now that we have the vector written in its real and imaginary parts, we need to write e to the negative 2 plus 3it in its real and imaginary parts. To start, we'll distribute the t in the exponent. E to the negative 2 plus 3it is equal to e to the negative 2t plus I times 3t. And this can be rewritten as e to the negative 2t times e to the I times 3t. Now, the imaginary piece e to the I times 3t we've worked with before. Remember, we can split e to the I times 3t into real and imaginary parts using Euler's formula that says e to the iz is equal to cosine z plus I times sine z, where our z here is 3t. So we can rewrite e to the I times 3t as cosine 3t plus I times sine 3t, which is still being multiplied by e to the negative 2t. Distributing e to the negative 2t in, we get that e to the negative 2 plus 3it can be rewritten in its real and imaginary parts as e to the negative 2t times cosine 3t plus I times e to the negative 2t sine 3t. In combining these two things, we get our complex solution rewritten as y sub c of t, which is e to the negative 2 plus 3it times the vector I1, is equal to e to the negative 2t times cosine 3t plus I times e to the negative 2t sine 3t, which came from that exponential written in its real and imaginary parts, all times our vector written in its real and imaginary parts, 0, 1, plus I times 1, 0. We still have a little bit left to compute though, because although each factor is written in its real and imaginary parts, we haven't completely written yc in its real and imaginary parts. So we will need to distribute to split yc into its real and imaginary parts. Distributing in yc, we get that yc is equal to e to the negative 2 times cosine 3t times the vector 0, 1, plus I times e to the negative 2t cosine 3t times the vector 1, 0, plus I e to the negative 2t sine 3t times the vector 0, 1, and finally plus I squared e to the negative 2t sine 3t times the vector 1, 0. Now remember, we want to split this into its real and imaginary parts. We'll start by getting the real parts. E to the negative 2t cosine 3t times the vector 0, 1 is completely real, and I squared e to the negative 2t sine 3t times the vector 1, 0 is also completely real because I squared is negative 1. So we have e to the negative 2t cosine 3t times 0, 1 minus e to the negative 2t sine 3t times 1, 0. For the imaginary part, we want to get the terms that have I as a coefficient. Those are I times e to the negative 2t cosine 3t times 1, 0 plus I e to the negative 2t times sine 3t times the vector 0, 1. In factoring I out of both of these terms, we'll get that the imaginary part is e to the negative 2t cosine 3t 1, 0 plus e to the negative 2t sine 3t times 0, 1. To simplify this a little further, we can combine the real parts into one vector and the imaginary parts into another vector. E to the negative 2t cosine 3t times 0, 1 is going to give us e to the negative 2t cosine 3t in the bottom component of the real part, and negative e to the negative 2t sine 3t times 1, 0 will give us negative e to the negative 2t sine 3t in the top component. Similarly, we can rewrite the imaginary part as e to the negative 2t cosine 3t, e to the negative 2t sine 3t. So now we've found the real and imaginary parts of y sub c of t. And before we put together our general solution, I again want to remind us that despite its name, yi of t is a completely real function because it just has I as a coefficient, but not part of yi itself. So based on the theorem we just saw, both the real part and the imaginary part are solutions to the system. And since we have these two separate solutions, we can use them to build the general solution, which will be y of t equals c1 times our real solution, negative e to the negative 2t sine 3t, e to the negative 2t cosine 3t, plus c2, e to the negative 2t cosine 3t, e to the negative 2t sine 3t. So we started out with a completely real linear system of differential equations, had to pass through some complex reasoning because our eigenvalues and eigenvector were complex, but eventually found a general solution that was also a completely real solution.